All right, so up next we've got Dave Armstrong. Dave is a Director of Business Development at Advantest, where he is focused on developing and delivering manufacturable test solutions to meet our industry's newest and most demanding test challenges. Dave is also chairman of the Test Technology Working Group for the Heterogeneous Integration Roadmap, where he works hard to try and really pinpoint the industry's disconnects and trends and feeds them back to not only his company, but the industry at large. With over 4 decades in the industry, Dave has had experience in the ever-changing world of IC design, system design, product development, yield engineering, test engineering. He's pretty much seen and done it all. Today, he's going to be presenting on the need to kind of reassess the overall impact of continuing the current trend of passing probably good die through the rest of the test and manufacturing flow in a world of heterogeneous integration and what that means to the overall final product cost and impact. So take it away, Dave.
Thank you, Mike. Probably good die. That's probably one of the most debated topics or terms in the industry. Mostly good die, sometimes good die. The way I look at it is the industry needs to morph and change, shift to the left, if you will. I see this as a big trend. Certainly not the first trend I've seen in my career, but an important one. So my goals for this presentation is to show you something you haven't seen before and give you some numbers for the value for it. So I'll start by talking about the trend, what's driving it, what are the implications for it, and then we'll get into briefly how you implement this shift left in your own test flow sequence. Also briefly mention the risks of doing this and summarize by talking the contributions this shifting will give you and your process and your devices, hopefully a better bottom line. So what is the trend? So I'm showed here what I think is probably a more typical device integration for multi-die assembly today. What we have are devices perhaps coming from 2 different fab lines, perhaps 2 different vendors. One might be large, one might be small. We then bring together a memory stack of some nature, assemble it together, and then we got to do final test and system level test. Well, this is the traditional flow, if you will. And, one step that, one change that is occurring is people are doing more system level test at the end. This is simply a cost minimization step, but certainly we're seeing a push to shift some test content to the right. My question is that the right thing to do? With this presentation, I propose that shifting test content to the left, final test perhaps to what I call known good die or wafer probe or system level test back to the left, is actually more financially beneficial to you and to the industry. But obviously, I got to prove that, so stay tuned. So before I do that, let me define some terms. I consider basically today us having 5 steps, if you will. Certainly there's the traditional wafer test step. It finds the easy to find rejects, the hard shorts, the opens. Typically, it does some scan functionality testing. It'll be done on the ATE with a wafer prober. What I call a known good die step could be done on a wafer prober, but it could also be done on a singulated die prober. I've seen both. And what this will do is it will confirm functionality and scan at a second temperature. It'll find assembly defects, all the things that Bernice was just talking about, the delamination, the shorts. A lot of those things will pop out of this second step if you do it after singulation and die selection. So I look at this as 2 initial steps prior to packaging, which would then give you a final test step. So here you have the packaged device, you do more scan tests. Certainly you're going to do your parametric testing, especially if you're doing an RF device. At speed tests, high power tests are very common here, as well as some stress tests. Equipment complement would certainly be the ATE, and add to that some active thermal control. Really important for you to have the thermal control. And then you'll do it on either a device or die handler, depending on where you're doing this test step. Final step is certainly system level test. So here again, we're doing it at the package level. Boot up tests are typically very important here. And here you're using SLT, and again, an automatic thermal control and a device handler. So what I'm going to be proposing here is that we shift left. We take system level tests and bring them back to final. Or we take final tests capability and shift it back to known good die. Obviously, both of these, or all of these, bring with it the challenge of how do we bring the test cell capability back in time. Oh yeah, one more, we can take known good die, do the second test step at wafer probe as well. So why is this happening? Well, I think a lot of us realize that more tests sooners make a lot of sense and can have a lot of value. So here I've just shown one path through that flow. If we can simply increase our failures or increase the bad parts that we should be finding at wafer probe by enhancing wafer probe, obviously our profit is going to grow, no question. Additionally, another thing that's happening is heterogeneous parts are really complicating how all this goes together. So we need a higher level of quality before we do the multi-die integration, or else our profits are going to shrink. Guess I could have animated that, but. And finally, one other big trend that's happening is different vendors are providing known good die to other vendors. So all of a sudden we're shipping product much sooner in the flow. So now your company's reputation is on the line for the parts that you just shipped. And guess what? You may not have done all the tests that you used to do. How do you make sure that you do those? Shift left is the answer. So unfortunately, there's some realities of known good die. And I decided to cover these as questions, hypothetical questions. For instance, if I get a 90% yield at wafer probe, what's the percentage of possible fault? What percentage of the possible faults did I uncover? Think about it for a second. Here's the answer. Yield only states the percentage of the parts tested were bad. In fact, you may have uncovered 0% or 100% of your faults. Passing parts are certainly not guaranteed to be 100% good. We all know that, or else we wouldn't be doing more testing. Similar question, if I spend 10 seconds of test time to get 90% yield with a really good fault coverage, we did our DFT really great, how much time and fallout must I spend to get all the failing devices? Well, there's something called the law of diminishing returns, and you need more time to get more coverage, and realistically, it's an exponential curve from my experience. And it never really gets to 100%. So obviously we need to do as much as possible. And I tried to show that on this next slide. So this is showing a model that I'll be using for the cost analysis. Here, what I've done is looked at what I would call a small part. Small part, you might get 90% yield on the first test and it might only take 10 seconds. So the next test step, this would be the known good die step perhaps. You probably get half the remaining failures, but it's going to take longer to get that. So basically I'm just saying, hey, let's have the remaining failures each time and double the test time, giving us a curve like this. Notice it never really gets to 100%. So one way of looking at this is which faults did we actually catch? Well, the first test step caught all these faults. It's the area over the curve is what we found with that test step. But we didn't find all these other failures that are exponentially or lingering. So as we move out further and further, obviously we'll get more and more with each test step. And realistically, unless you are there forever in some cases, you're going to have some undetected faults. And based on this model, that's probably 1 minus the yield. So in this case, it'd be 1.25% of the faults were not fully detected here. So this is fine for a small part. What happens with a large part? From my experience, a large part is going to start out with a lower initial yield, and it might still grow, you know, have the remaining failures per step and double the test time. So, you know, by looking at these two types of parts, we can start making some conclusions. That's where we're going to go, is look at the cost associated with these die as well as the test time and everything else. So in doing that, rather than actually using dollars and cents, what I'm going to do moving forward is ratio everything, basically normalize it to the cost of a small 10 by 10 millimeter die. Why am I doing this? Because you may have different process nodes that you're on. You may have different pricing, and relative pricing between a small die and a 30 by 30 millimeter part is, or that's 25 by 25, is relatively consistent, even with regards to process nodes, in my opinion. But so by using this normalization technique, I think it removes questions, and I think will enhance your understanding. So any questions about what I'm doing?
So,
yeah, Mike.
Yeah, actually, we do have some questions. And just a reminder to everybody, please type your questions into the Q&A block if you can. That would help us out. So an open question right now, and I know you've had some experience with this in the past dealing with you personally from AMD. The question is, can you explain if system level test can actually be shifted left to final test and, you know, effectively eliminated? What types of coverage couldn't we remove from SLT and move into ATE, and what are we leaving on the table?
So I don't know what can't be shifted. I don't have a full answer to that. I can state unequivocally that it's damn hard to shift everything to the left. Memory emulation, for instance, is one thing, or memory, adding the memory so you can do a full boot is very, very difficult. But an awful lot of the rest of the tests can be done prior to SLT. I would say that's a work in progress, Mike. A lot of people are working very hard at that, and it's really fascinating to watch.
And I think inherently what you're saying is that you want to limit the amount of time you are spending in the right shifted test insertions, knowing and being realistic with the fact that it's impossible to get to 100% KGD. Absolutely. It may be 100% of your desired KGD target, but relying on constantly pushing the tests out further in time is more the argument you're making. Well, we shouldn't be doing that. We should be trying to pull as much in as we possibly can. Is that a correct way of saying it?
Well, I mean, it's sort of like, what is a known good die? It's a percentage good. What is a known good, a known shifted SLT? Well, it's not going to be 100% shifted left, but can we do 75%? I think so. You know, can we do 90%? Probably not. It's a percentage. And I do think that the tools, the methodologies are going to grow over time and change over time.
Lots of questions coming in for this shift left concept, which is good.
Okay.
Cool. So the actual question I see is are we finding it harder to shift left with the
Mike, you disappeared. Hold your question.
Sorry, my Zoom died and then it rebooted and it came back muted. The question I got is, have you found it harder to shift left with frequencies increasing, such as millimeter wave for 5G, or any of the RF technologies that have been going on? Is that becoming more and more difficult to do at wafer?
I think it's becoming more important to do, and certainly more expensive to do. And you know, I've been amazed at how our industry is able to overcome barriers and hurdles. I don't consider any of these as brick wall barriers. It's simply a matter of cost.
Okay. Please continue. I don't want to take up all your time with questions yet. We'll do that at the end.
Okay. So here, I wanted to look first at a small device, and I have two tables here, one without shifting left and one with shifting left, using that example yield curve that I showed you before. Some of the characteristics that I use for my assumptions are shown on the left, number of die per wafer, et cetera. 10 nanometer came in because I actually know the cost per wafer for 10 nanometer and can do some calculations here. So if we have our wafer, comes in with 650 die locations. If I have 90% yield, I'll yield 585 parts, which move forward. The cost here is mostly the cost of throwing away these 65 die. Basically 10% of this cost is throw away those parts and add that cost onto the 585 die moving forward. Actually, it's more than 10%. So the other cost is certainly the test time and the equipment and everything else. It's a fairly elaborate model that I've gone through here. Now, if you take these 585 die, you put it through thin bump and sawing, typically assembly people say that's like a 99% yield type step. So you have a little bit of cost hit there, a little bit of parts go away there. Then if we go through the second step, a singulated die test in this example, you might have 95% yield and 29 parts you might catch, and you end up with 550 going out the door. Now, since I wrote the model, I know that some of these parts are still faulty. And so I put that here just as a placeholder to say, hey, the model says that we didn't find all the failures. Obviously, your mileage may vary, but just to be clear. So let's see what happens if I shift left. Let's say that I do my known good die testing at wafer probe. What that will require is I'll need to do 2 temperatures on my wafer, maybe step over it twice, whatever. But what I've done here is I've said, okay, I got 10 seconds for step 1, 20 for step 2. So I have a 30-second test step here. My yield now is the product of 90 times 95. So that's actually less, 85.5, which is good news because we've actually found more failures. In fact, 94 failures, which again is the sum of 65 plus 29. It cost a little bit more, sure. And a large portion of this again is the failures that were found by doing this step. Moving forward, similar amount of parts going through assembly, similar amount of failures, similar amount of cost. Now all of a sudden you start seeing a big change for the known good die test step, the next step. So now if you're doing more functional type testing here, you're going to get much better yield. Of course, you're going to need a higher test time, but you're going to have fewer failures because you found more failures before. And that trend continues, and you would have fewer failures out the door, but also you'd have fewer parts out the door, which I think is good. In fact, this shifting left reduced, based on this model, failures by over 50%. And it only caused the cost to manufacture to go up by less than 10%. To me, this is a pretty straightforward no-brainer. Take as much time as you can at wafer probe to find as many failures as soon as possible and bring final test content back into known good die. By the way, I know some of this is controversial, but let's save the questions until we get through the next 2 slides anyway. So in a large device, bigger part, fewer die per wafer, so the cost is higher just to start with. Again, I'm normalizing to the cost of the small part. Here we have 70 lower yield, as we discussed before, longer test time, so higher cost for that. Thin bump saw, that's the same. Known good die would be similar. I think you can see how these charts go together, and you end up here with a similar improvement in quality of parts being shipped out the back end, if you will. And a similar small increase in cost to manufacture. So far, everything is bearing out, and it's looking like, hey, better quality for not a whole lot more cost. So now let's do a multi-chip module. I have some assumptions here. Of course, your mileage may vary. So here I thought we would look at building 100 MCMs with 10 small die and 1 large die. No HBMs on it. So we'd have 10-to-1 ratio here. We have the cost that we pulled forward from before without shift left and with shift left. So these are just pulled forward from the previous slides. So now we do our multi-die assembly. 99%, actually it's per die assembled is typically, but bottom line is you're not going to have much fallout there. No, I just did 1% across the whole assembly. Sorry, I didn't do per die. Final test, different yields, different test times, and different yield numbers, because here, this is the traditional final test that you'll be doing today, and long test time because you have 10 die that need to be tested with test time 1, and 1 die that needs to be done with test time 2. So I've actually cheated a little bit here. I didn't include the die-to-die interconnect test and all that kind of stuff. This is sort of the minimum that you would have at this pot, in my opinion. And you'd have a certain yield, which is based on the product of the yields of the various die that's in play. Now over here, what you're going to do with the shift left is, yeah, you're going to do more more system level test content. And in reality, as the question alluded to before, it's going to be reduced system level test content. And in reality, you're going to need another test step to check for final test assembly, shorts, opens, did everything make connectivity. But the bottom line is your test time will be significantly higher at this step, and your system level test time will be significantly reduced. Certainly not eliminated 100%. So what do we end up with? Well, because you have higher quality product going into your multi-die assembly, your cost to manufacture is down a lot. That's a major aha. So taking and shifting your tests as early as possible, especially prior to multi-die assembly, will improve your quality and reduce the number of parts that you have to test. And in the end, you're going to end up shipping more good product out the door. Now, Mike, in the interest of time, we will have, I guarantee, a lot of questions around a lot of this analysis. And happy to talk to people individually on the details, and maybe you can help summarize as we move forward. But why don't we try and finish off the slides, because time is a-flirting. And
yeah,
then, okay, so what is needed for system level test? What do we need to do to shift final test into known good die? I think this is one of the questions. Well, we'll be doing more at-speed testing, and probably more importantly, we have to bring an automatic thermal control, a die-level thermal control, into this test step. Something that can be done with singulated die handlers for sure. And I question whether it can be done with a frame handler, because there you have sticky tape in the middle, and you certainly have a lot of parts and a big chuck you got to move the temperature of. So there are ways to doing this. And as well as alluded to in one of the questions, sure, you would need some high frequency probes if you're going to do at-speed testing. Do you move 100% of the test forward, or look at the cost trade-off here? One of the things that you're definitely going to need is you're going to need to cover or carry more current into your part. So you're going to need some higher CCC probes, good thermal feedback. Perhaps you might want to reconfigure your ATE for higher power, supplies, and instruments. Known good die into wafer test. Here, as I alluded to before, you're going to need 2 temperature testing at wafer wafer probe in this case, first step. And now you're going to have a longer test time, and the temperature change, you got to be able to handle somehow or another, because probes don't like it if you change the temperature while you're down. So it's much more complicated. Moving system level test, and this is one of the questions already, into final test. Certainly you're going to need high temperature ATC, some high speed interfaces, and Do you do boot up? Not. Do you need to do memory emulation or put memory chips on your interface board? A lot of trade-offs here, but I maintain that a large percentage of system level tests can move forward. I'll just leave it at that in the interest of time. So what about over-testing? So today we basically do 4 separate steps on some high performance devices and multi-chip integrations. I maintain that there's a lot of overlap. I wonder how many times we check static power supply current on die 3 and the like. Certainly there's a lot of scan tests that get repeated. Certainly if you go to fewer steps, you're going to end up with less overlap. And by the way, you're going to end up with less handling. Some people just say, hey, the handling alone pays for any of this stuff, because each handling step is a yield loss. So what have I tried to do in the time I've had? 1, I believe I've shown that test itself is a valuable resource. And we need to look at where to best deploy it. And this is a question that's changing. This is where the roadmap team is talking about a shifting in our test sequence. Basically, we have to look at what the economists look at is the maximum value. Where can you get the maximum value per step and deploy it there? I believe I've confirmed what is obvious, that more tests sooner will significantly improve your quality of parts that you ship, and it can be done so at a small increase in product cost. We've done some calculations that known good die product quality will improve if you do this. And as I said a minute ago, it's not that expensive to do. Shifting test content to the left 1 step will improve your multi-chip module yield. And also it will help you get good multi-chip modules sooner. Time to market. Why? Because you know the product you're assembling together is of a higher quality. You know that you have a higher probability of meeting your ship commits because the product's going into the multi-die, multi-chip assembly is higher quality. Additionally though, I've shown that it's lower cost to do that. Finally, I pointed out some changes in the test equipment. And yes, some of these are not cheap, but some of them can be. And these need to be considered in order to do this. It's a really gray zone area, but it's a gray zone with a lot of potential value when we confront it actively. I say it that way because I don't think it's an if we confront it. I think we have to as an industry. That's it.
Thank you very much, Dave. Some additional questions that have been going on in the background and kind of fed in with some of the questions that I had too is as we shift left and as we move things from the unpristine or impristine environment that is SLT into something like ATE, where we're very focused on receiving samples by clock edges and stuff, what's your feel and take on the introduction of false failures? Something that may not be good enough to pass on ATE, but actually would have passed SLT and sold because there was enough slack or something, as we've talked about many times, like AC scan, that clock trigger can induce such a power droop event inside the device that you don't actually pass at speed that you thought you would, but in a system level environment running at that speed, you'd never elicit that type of droop event and all of a sudden you pass. So are we going to be overcutting on the actual device parametrics themselves beyond just coverage from test insertions?
I think you're almost repeating the question I had for Zoe yesterday. And it's a fascinating question. I don't know that I have a good answer for it because I was asking it as well. However, let me flip it around. And I have heard people, customers say, hey, SLT environment is noisy, but real world. And if you take SLT and move it into the ATE, it's going to be too damn quiet. I'm not going to get the same failures because you're doing too good with your power supplies. My brick in the PC is not that good. So I don't know the right answer. It's
Trade-off, yeah.
It's definitely a trade-off, and we're not at the sweet spot yet. That I can definitely say.
Herb has a question, just generally, have customers' feedback confirmed any of your numbers here, or any of your thought, at least from a trending perspective?
Yes, definitely.
Excellent.
A trending perspective for sure. I have a cost of test spreadsheet that's sort of a bestseller in the industry. And it really does help people realize, at least first guess, where the best test value can be achieved.
Good. Yeah, okay. And then finally, the last question, actually, we got through all of them and right on time too. There's a question about and so actually, it says, could AI be utilized to shift left? And actually, I think this would be an amazing panel discussion between Zoe, you, and Jeff from tomorrow, just sitting together and having an interesting conversation about how that could fit into the world. But what's your gut take on that right now?
So data sooner is just as good as test sooner. So if you can do a wafer probe test that AI analyzes to point to this failure or that failure, I think you're making progress. So I definitely see a big, good role for AI. However, let me temper that. The problems that Bernice was showing in the previous presentation, I don't know how many of those we're going to find with AI. We're still got to do the core testing to find some of those shorts and opens and everything else. Or maybe we don't. Definitely, this is an area of opportunity for us as an industry. And I wish I had a solid answer. Sorry for being wishy-washy, but I definitely think AI is going to change the perspective of the industry moving forward, no question. But it's definitely not going to get rid of test.
Excellent. Thanks, Dave.
So thank our sponsors once again. Our diamond sponsor, ASC, providing design, assembly, tests, materials, and components, logistics services to the electronics ecosystem through their different entities. So thank you, ASC. Thank you, Advantest, global leader in ATE, doing the heavy lifting of the testing to make all these advanced technologies available and reliable. To GelPack for solutions that allow material handling, both in fab and transport of very valuable devices. So thank you also to GelPack. And lastly, thank you to Mulbauer Group in terms of factory automation and material handling. So thank you for sponsoring this event and making it possible. I want to remind everybody that the final session is tomorrow morning, Friday, September 18th from 8 to about 10:30 a.m. Pacific time. We'll talk about solutions in particular. Your Zoom link that you used today is good for tomorrow. You'll also get a reminder. And with that, but I thank everybody for joining us today, and I wish you a good rest of your day and look forward to having you join us tomorrow. Thank you.